Okay, class, welcome back. Today we're in lecture 7 and we're talking about more applications. So the first one we're going to talk about has to do with temperature. And so we are going to write down a law, and pen is being weird, and of cooling, and then use it to describe a situation using a differential equation. So this is called Newton's law of cooling. And the idea is that how quickly or how fast an object's temperature changes is proportional. So the keyword from last time, proportional, will tell us something in a second, to the temperature difference between the object and wherever you put it. So we call wherever you put it the surrounding medium. So that could be like the air temperature, or if you dunk it in water, the water temperature. So that's the idea. So how quickly an object's temperature changes is proportional to the temperature difference between the object and the surrounding medium. So this, as a differential equation, says what? Well, first of all, the temperature is changing, and it's changing over time. So I need to call temperature something. So I'll call it capital T, and it's a function of time. And this is the temperature of the object after some time has passed, time being little t. So it's what we're trying to figure out because it's the thing that is changing. And so, of course, that change is called the derivative. And so we're going to need that. And that is proportional to something. So it's going to equal something. So it's proportional to something, meaning it's going to equal a constant times something, just like last time. But now, what's different between this one and growth and decay is the something is not just the current temperature, but it's the temperature difference between the object and the surrounding medium. So the temperature difference, that just means the subtraction of the temperature of the object, which we already named as capital T, and the surrounding medium. So I need to name that. And I guess I'll write the name down over here. I'm going to call it T with a subscript M. So this is the temperature of the medium. So how quickly the object changes temperature, the derivative of T is proportional to K times T minus Tm. That's the temperature difference. So that's what's going to go here. And typically what you do is you assume that this is just some constant number, some given number, like the room is 100 degrees or 0 degrees or something like that, or the water is that cold or hot. And so you just go ahead and plug that in there. But in any case, this is the differential equation describing the situation. It is separable, but it's also linear, so you could solve it 2 different ways. Usually separable is easier. So I'm not going to do that for you here, but if you wanted to, it would be something like this. And then you would integrate. Okay. So in any case, that's something we can solve, and then you'll get a nice little formula for the temperature after time t. I think it ends up being, don't quote me on this, but it's in the lecture problems, correct at least, but here it might not be. So I believe it ends up being something like this, CE to the KT. So it looks very much like a growth and decay formula, except there's this extra bit here, some constant that's just being added. And then this sort of looks like the growth and decay formula. But yeah, I believe this is what you'll get. Okay, so we'll deal with that in the lecture problems with specific examples. But the point of this is to just give you some other examples and not go into too many word problems with them. but just to get through a bunch to see the cool things that you can model with differential equations. Okay, so the next one is electrical circuits. Now, if you've taken a physics class, you've probably learned about these, and they can be very difficult to learn about. So let's try to understand them pretty slowly. So we're just going to study one basic type of circuit, but basic premise is that circuits are made of wires and a bunch of electrical components. Typical ones that you see are resistors, inductors, capacitors, and then there's usually like a battery. And what we do is we draw these components so that we can draw a diagram of the circuit without actually building the circuit. We just make a circuit diagram to study what's going on. So a resistor looks like this in the diagram. A capacitor looks like this. And inductor looks like a little squiggly guy like that. And then there's the battery, which just looks like this. So what you do is you draw a circuit by sort of connecting these together in various ways. So one example of a circuit is something like this. So I have a battery, I'll have a resistor and an inductor maybe, and then I'll loop it back to the battery. So this is an example of a circuit, and it's called a series circuit, but we're not going to worry too much about the difference between series and parallel for now. But then what's going on is that the circuit has, well, it has sort of like mass, but it's for electricity. So it has something called charge. And you should sort of think of this analogy, sort of like a falling body has mass. And if the body is not falling, if there's nothing pushing on it, well, then it's just sitting there, just sitting on the ground. If there's nothing making it move. Similarly, the charge is just sitting there in the circuit until you turn on the circuit. And what does it mean to turn on the circuit? Well, for a falling body, let's do that first. The idea is that a force is what really moves the mass. And you can think of it as like giving life to it, but that's called velocity for force, or for the falling body problem. So a mass just sits there until a force comes along and pushes it, gives it velocity. Similarly, the charge is just some thing that the circuit has, but it's much harder to visualize than a object having mass, like a little blob or something. But it's the same idea. It has this charge, and then the battery acts like the force, but it's called a voltage instead of a force. Maybe I'll box with the same color things that correspond. So then the idea is that a voltage gives life to the circuit. And so the voltage moves the charge, and it's very similar. So the mass begins to move with some velocity, but now the charge begins to move instead of with velocity. You call it current. So it gives the charge current. So you think of it as it starts to move around the circuit instead of just sitting there. So this analogy will serve us well. We're going to think of velocity as being like current, voltage as being like force. It pushes the current. And in the falling body problem, the goal was to figure out this thing. Figure out what is velocity at time t using a differential equation. And now we are going to figure out the current. But current, we don't call it C, like velocity makes sense because it's V velocity. Current, we call it I. It's because C is taken by something else. We'll see later. So this is going to be the current after time t in the circuit. It's going to act very much like velocity does. Okay, so our goal is to figure out this function. And then we're going to have some laws that tell us how things work. Okay, so here's the idea. So we'll think about this force voltage analogy first. So this is what we're going to look at first. Okay, so a battery gives a constant voltage, which we'll call V. I'm not going to worry about units. The units are very confusing for me in electricity. I'm no physicist, so I just take them out. I don't care about them. Okay, so a battery gives a constant voltage, V. So that's what's pushing the current, giving life to the charge and creating a current. And then these other components have voltages too. So what we do is we can calculate the voltage across the components. So across a resistor, you would call that V sub R. That's how much voltage is across the resistor. So there's like another way to think about voltage as potential difference, which also has analogies to force, but I don't want to get too much into it. We're just going to take this as a little fact that there's a voltage across the resistor. There's a voltage across an inductor. And the letter I is taken, so it's not going to be called V sub I, it's going to be called V sub L. And the way these relate is sort of how, it's very much how force worked for the falling body problem, in that the sum of the forces add up to the total force, and now the sum of the voltages will add up to the total voltage of the battery. So that's a nice little thing we'll get to use. Okay, so then the law we get to use is that the sum of voltages across the components equals the voltage that the battery is providing. So if the battery has voltage V and there's a VR voltage across the resistor and a voltage across the inductor, then those two added up to give you V. So you should compare it to the falling body problem, which said that the total force on an object equaled the sum of the forces, but in that situation we had two forces, gravity and air resistance. Very similar. And afterwards, then we realized how to write these in terms of velocity. And so that's what's going to go on here. Now we're going to bring current into here. So in terms of current. Okay. So that's where more laws come in. So a resistor has resistance it's a property of it called R. And then voltage and resistance and current are all related together by this law. So the voltage across the resistor is equal to the current times the resistance. So it's very similar to air resistance. So air resistance was proportional to the velocity. So you could just think of it as the constant going in the front instead of the function of time, and then the analogy comes together there. So these two are sort of acting the same. Okay, and then an inductor also has an interesting property. It's a little bit different. So an inductor has, instead of resistance, it has an inductance, L. And it's just some number. So R is just some number that you're given ahead of time. So is the inductance of the inductor. And it's related to the voltage across the inductor, not proportional to the current, like up here. This one is proportional to the current using the resistance, but instead proportional to the derivative, how quickly the current changes. I don't know why I put that there, d/dt. So it's a bit, so this law up here is a bit weirder, because this is sort of saying like which force does this compare to? Well, this is more like the total force, which was m times dv dt. So it wasn't like this one is not like gravity, like you might expect. It's more like the total force in terms of this analogy. So these two sort of go together. Gravity was very much like a constant, because it's just m times g, and m, the mass is constant, the gravitational acceleration is constant, and that's very much like voltage, because voltage is just this constant that the battery provides. Okay. So then, using these laws, V equals VR plus VL becomes something else. Well, V is just the constant voltage of the battery. That's not changing, but VR is now IR, and VL is now L di dt. So this is a differential equation telling us the current. On the current in the circuit that I drew before. And this is a linear one, so I can rewrite it as, let's see, so I want di dt alone, so I have to divide by that L, R over L I equals V over L. I believe that is what I want. Let me just check. Yes, okay, good. So just note how similar it is to the one for the falling body problem, which was, well, it started off as m dv dt equals the gravity plus the air resistance, which was negative, and then you could rewrite it as k over m v equals g by dividing by the m. So they're very much of the same form, and it's because there is an analogy between what's going on, so it makes sense that that should happen. Okay, so in any case, this guy is linear. So this one I will solve for us. So I didn't solve the temperature one, but I'll solve this one. So we can use an integrating factor to solve it. So what's the integrating factor? It's e to the negative r over L integral dt. Everything's with respect to time. So this will just be e to the negative r over lt. So remember, r and l are just resistance and inductance. They're just properties of they're just numbers related to the resistor and the inductor. So those are just numbers. Okay, so then I multiply this integrating factor to this linear equation. And I use the fact that I'm really good at linear equations now to know that the left side just becomes the integrating factor times the variable. So instead of y, it's I, the variable that's dependent on the other one. So I is dependent on time. And on the right side, I just have this constant v over L, and I'm multiplying it by the integrating factor, and I'm integrating with respect to t. And then since everything is a bunch of constants, it's not going to be so bad as it looks. So this becomes, I have to divide by negative r over L, which becomes negative L over r. And then this stays the same, plus a constant. And then I can solve for I by dividing by the stuff. And also the L will cancel, so I just get negative V over R. Those cancel, plus C e to the R over LT. Am I off by a negative? I think I am. I think I'm off by a negative way back here. Whoops. Let me see here. Oh yeah, I didn't need to subtract. It was already on that side. So that's fine. Whoops, okay, so that's a plus. So then this is a plus, that's a plus. That's a plus, that's a plus. So that's a plus, a plus. So this is a positive V over R, and then this is now negative because I divided by it. Okay, so that is the equation. It tells us the current in the circuit at time t. And then usually what you do is you assume there's no current at time 0 because the battery just getting started, I guess. I don't know. So we assume no current, meaning it just equals 0. AKA initially, is the key word. So then that just lets us solve for C immediately. So 0 equals V over R plus C e to the 0. So then C equals negative V over R. And then you might plug that back in to say that the current is given by this equation minus V over R e to the negative R over LT. Okay. So it's a lot of background stuff to figure this thing out. Then an example is really just about plugging things in now, and it's not so bad. So let's quickly do a little example. So if like a circuit has voltage, again, I'm not worried about units too much. 5 resistor with resistance R equals 50, an inductor with inductance L equals 1, and no initial current, then find current at time t. And we already did all the hard work. So V is 50, V is 5, R is 50, L is 1. So my differential equation, oops, dl dt, sorry, di dt, yeah, all these letters. My differential equation just becomes this. So I'm replacing the voltage, the inductance, and the resistance with these numbers, but it's all solved the same way. And you'll just end up with the same equation, but now with these numbers specified. So V is 50 over, V is 5, I keep doing that. V is 5, R is 50, R is 50, and L is 1, T. So you just get this, which you can simplify if you like. 1/10 minus 1/10 e to the negative 50t. So this is how much current there will be in this circuit after time t. So notice there's sort of something like terminal velocity, but I guess it's terminal current. So as time goes to infinity, this will go to 0 because of the exponent being negative. So then the current will approach just this 1/10. So it doesn't just disappear, which makes sense because the battery is continuously providing more and is providing the voltage constantly. So the current shouldn't just stop ever. It never stops. It goes towards this, whatever this number is here, because this goes towards 0. Okay, so that's another cool application of differential equations. Let's do one more that I like a lot. It's very relevant to coronavirus, so modern day times. It's called logistic growth. And it's another type of growth. So we did basically like unlimited growth where something just keeps growing forever. So earlier we used dn dt equals kn to model growth. And then one thing you could say is it gives you exponential growth, because you get something like this. So this really models exponential growth. So the more time goes on, the bigger it grows, and it just goes up and up forever. So this is perfectly nice, but in real life, there's limitations. So like there's resources for a population of animals or something that's growing. So eventually something bad will happen if it grows too much, and it won't just keep growing based on the current proportional to the current amount. Something else will happen. It'll have to have some limiting, some way to model limitations. And this happens with the coronavirus too. So any sort of virus that spreads, eventually there's nobody left to spread with, so it can't just grow forever. So how can we deal with this? So now what about limitations, i.e. We still want proportional growth to the current amount, but we want to assume that the population cannot grow forever. Want to stop population from growing forever. Just because that's more realistic. Most things can't just grow forever. So there's several ways to do this. We'll do one way here called logistic growth, but there are other methods. So one way to model growth with a limiting amount is to use this differential equation. So we'll see why it creates a limiting amount in a second, but first we'll write it down. So instead of just having a constant, so A is now the constant instead of K. Instead of just having proportional to the current amount, we subtract another proportion to the amount squared. So we do minus some other constant. So A and B are both just sort of like K acted last time. So these are just constants. So why does this give us growth with a limiting amount? Well, first of all, A needs to be bigger than B, the numbers, for this to be happening. So you can think about it like a function, just to look at it real quickly. So like 10x minus 2x squared is going to be some sort of downward parabola. But because the 10 is bigger than the 2, it's gonna like it's gonna be able to go up a bit first into the positive area of the graph. So something very similar is going on here. So we need A to be bigger than B. And then this will cause dn dt to be 0 at some amount for n. So do you see why and why this is what we want? So first of all, this happening, if the derivative is 0, the growth is 0. This is really saying that the amount n of t stops growing because the derivative is the rate of change. So the derivative hitting 0 is telling us that the amount stops growing. So this creates a limiting amount. But for which amount? And why does it do that? Well, all we got to do is factor. That's the key. So it's because if I have this as my model for the rate of change, then I can factor out an n, and then at one specific amount, if this becomes 0, that makes this be 0, which makes the derivative equal 0. So when would this equal 0? Well, I just have to add and divide a over b. So this amount is the limiting amount. So when the population hits this amount, the derivative will become 0 and it'll stop growing. And then this is a separable equation. So it's a bit annoying to solve though. So I can just divide. Let me write it like this better. I can just divide this an, I guess I'll keep it factored out, n times a minus b, and I can divide that out, and then on this side I just get dt. So it's separable, and then you'll need partial fractions. To do it. So in the lecture problems, I will do it for you, so I won't do it here. But it's doable. It's a bit annoying. But in any case, so what this does, you'll get some formula for the amount, which has built into it this ratio of a over b being a limiting amount, which causes the derivative to be 0 when the amount gets to a over b. But instead of giving you the function, I'll give you that in the lecture problem instead. One thing we haven't done too much is thought about graphs. So instead of giving you this, let's think about what the graph of n of t might look like if it's behaving in the way we want. So the idea is pretty neat. So we haven't graphed solutions of differential equations, but you can do that. And we could have done it in the other applications in the lecture problems. I think in the previous lecture problems, we start doing that. But here, how might this graph look? So what's the idea behind this type of growth? Well, there should be some initial amount. That's when you plug in 0. So this would be n of 0 because I plugged in 0. So whatever this amount is here. And then the amount should be growing. And it's actually going to grow exponentially at first. So it's going to look a bit like an exponential graph. But then eventually it should hit, there should be some sort of limiting amount. So this is what a over b would be. So it would be some line which this graph dare not cross. So instead what's going to happen is it's going to sort of act like an asymptote. It's going to just follow it and get closer and closer forever, but it's never going to reach it. And that's what the graph of this function will look like. We can guess that without actually knowing the function, just by understanding really the differential equation and how it creates this limiting factor at a over b, where it stops growing. Okay, so that's going to be it for the applications. But there are lots more that you can look up, though we skipped a few, but these are the ones I like to do. Okay, so see you next time.